Good day everyone, my name is Ron and let's answer some thermodynamics problems. Consider 5,000 kg per hour of an equimolar ethanol and acetic acid binary mixture are heated at 101,300 pascals. The initial temperature of the mixture is 293.15 Kelvin and the pressure of the feed stream is 110,000 pascals. Calculate the heat requirement if the mixture is heated to 313.15 Kelvin. How about if the mixture is heated and saturated vapor is produced? So we have two required. One is what is the heating requirement when we heat a liquid to a liquid, and the second is what is the heat requirement if we heat a liquid to a gas. So this is the diagram and given required for the first part. So for liquid-liquid heating, the inlet is as follows, the details. So 110,000 pascals, 293.15 Kelvin, and the mass flow rate is 5,000 kg per hour, and the outlet is 1,300 pascals and 313.15 Kelvin. Efficiency details. Since the problem does not state a heater efficiency, we shall assume to be 100% or eta equals 1. I almost forgot that the molar fraction between acetic acid and ethanol is equimolar, meaning 0.5 for ethanol and 0.5 for acetic acid. Then for the given required for B, for liquid to gas heating, the same details as the inlet, the same details as the outlet, same efficiency details. We just need to take note that the outlet is a hot saturated vapor mixture. So for the outlet for A is hot liquid mixture, but for the outlet for B, it's a hot saturated vapor mixture. Then let us try to solve this problem using DW-Sim. So going to DW-Sim, let's go create a new process model. Then to initiate the problem, we need to set our boundaries and conditions. So going back, one of our components is ethanol. So we will write here ethanol. Then the next component is acetic acid. Okay. Then we need to check if it is correct. So we have ethanol and acetic acid added to our compounds. And that's the only compounds here. So we'll go next. The property package. Here's a rule of thumb. When dealing with water components only, use steam table. When dealing with gas components only, use Peng-Robinson. And when dealing with liquid components only, such as this sample problem, ethanol and acetic acid are in a liquid mixture, we use NRTL. So we'll use here NRTL. So I haven't added the NRTL, I'll add it later. So the system for the units in this problem, the mass flow rate is kilogram per hour. So we'll just set it here, change a new folder, kilogram per hour. Then for the pressure, it must be Pascal. So we'll put here Pascal. We'll also put the pressure difference as Pascal. Next, the temperature is at Kelvin. So we'll put here Kelvin. And that's it. Finish. And since I forgot to add the property packages here, this may be a lesson to you all. You can get also edited here in the settings. Go to thermodynamics and go. I chose NRTL for liquids. Then we add it already in the system. That's it. Simple as that. Next, the unit operation noting about here is all about heaters. So we'll go here to exchangers, heater. Then DW-Sim will automatically provide you the input and output streams. So let us name these respectively. So this stream, we'll be renaming it as inlet stream. And this stream, we'll be renaming it as outlet stream. And this one, we'll be renaming it as heat requirement. Okay, so let's condition. So the inlet conditions are 5,000 kg per hour. So we'll put here 5,000. Then mixture heated at 101,300 pascals. So this is the initial pressure, 101,300 pascals. And initial temperature is 293.15 Kelvin. 293.15 Kelvin. Apologies. It is not initially at 101,300 pascals. It is the initial temperature is 293.15 Kelvin, and the pressure of the feed stream is 110,000 pascals. I misread, but this is actually the initial pressure. So 110,000 pascals. Let's go back here to the diagram. It's more easier to identify. Then, the compound amounts must be equimolar. So ethanol must be 0.5 and acetic acid 0.5. Double check if this is mole fraction. Equimolar, mole fraction, half-half. Alright, set. Next. Then for the heater itself, we assume that its efficiency is 100%. So we'll put here as 100. The pressure drop. So we need to calculate the pressure drop or the outlet pressure in order to the pressure drop value to make the outlet pressure 101,300. So in order to do that, we just simply do a subtraction operation. So 1,100 minus 101,300. I'm writing the formula in the here to assist you all. So we have a pressure drop of 8,700 pascal. To double check, the outlet pressure here is at 101,300 pascal, which is the needed one for our heater. Next, we need to find the outlet temperature. So the outlet temperature, so the calculation type must be outlet temperature. Outlet temperature must be 313.15 Kelvin. And this is what we get. So as a result, so double check, the outlet temperature is 213.15 Kelvin and outlet pressure is 101,300 pascal. Everything is set. Then our heat requirement for a liquid heating is 47.94 kilowatts. How about the second question? If the outlet is a hot saturated vapor mixture, well, we don't need to change that much because we just need to go back to the heater. And do you see this? This is outlet vapor fraction. So when this is 0, this means that the outlet is all liquid. But we change the calculation type to outlet vapor mole fraction and we just change this to 1. This means that the entirety of the liquid stream going in the heater transformed into vapor at the outlet. 100% transformed into the vapor outlet. So we'll put here as 1. Enter. And we get a heat requirement when turning liquid inlet into a gas outlet, 1009 kilowatts. So that is the DWSIM simulation. So heated liquid mixture, 193.31 kilowatts. Yes, 193.31 kilowatts. And the outlet temperature is 1009.14 kilowatts. Now, let's discuss. How is this answer logical? So, when heating liquid mixture, it is a much lower heating value compared to when a phase change occurs. When a liquid turns to a gas, it is a higher heating value. So, why does this happen? Well, it all comes down to sensible and latent heats. So, what does these heats mean? So, we'll go to the heating curve of water. This is a great example. So this is the heating curve of water where in its solid state, water is ice, then it turns into a liquid water, then it turns to steam or gas water. You can see the line as the temperature increases, the amount of heat is absorbed. So in this line, the water is a solid or ice, but when it transforms into a liquid, its temperature is constant. Same thing, when the liquid transforms into a gas, its temperature is constant at 100 degrees Celsius. What does this mean? What is this phenomenon? Well, this is what we call sensible heat. Sensible heat are the slanted lines. So, the slanted lines, which is this one, and this one, are referring to heat that is being absorbed without phase change. This is represented by the formula mass times heat capacity of the substance, not only water, but the heat capacity of the substance, times the temperature difference. Next is latent heat. The latent heat is the one that I have been referring to for a while ago. This horizontal lines. So the transformation of phase change, in a sense, this is phase change heat. So this latent heat is represented by the formula mass times the change in enthalpy. enthalpy of the final outlet minus the enthalpy of the inlet. In a sense, it's the enthalpy of vaporization if going from liquid to gas, or enthalpy of condensation when going to gas to liquid. So, going to this arrow, the latent heat is represented by the flat lines or the horizontal lines. Again, sensible heat is the slanted lines, and the latent heat is the flat lines. What does this imply? Well, the heat requirement without phase change, liquid start and liquid end, only uses sensible heat, having this formula on only. However, heat requirement with phase change, liquid start, if it starts from liquid and ends in a gas, it comprises both sensible and latent heat, meaning that the sensible heat formula is added to the latent heat formula. So QLL represents the heat requirement for liquid to liquid, and QLG is the heat requirement from liquid to gas or phase change. Therefore, if this is the formula for a liquid to liquid heat absorption, and this is the formula for a liquid to gas heat absorption, this means qualitatively that the heat absorbed, sensible heat or heat absorbed by liquid to liquid must be less than the total heat absorbed when transforming liquid to gas, as shown in the formula. It's proven mathematically that the amount of heat needed to heat in a substance that without phase change is much less than the amount of heat needed to phase change a substance from either solid to gas or solid to liquid or liquid to gas. In connection to the problem, our heat calculated for a liquid to liquid heating is 193.31 kilowatts, and our heat calculated for liquid to gas transformation is 1009.14 kilowatts. 193.31 is far less than 1009.14 kilowatts. And compared to what we discussed earlier, this means that our answers are logical. This means that the solution for heated liquid mixture is within theory that it must be less than the amount of heat needed to transform liquid to gas. It is due to sensible heat, and with phase change, sensible and latent heat. The energy requirement is simply the total heat or energy being put into the system. If for the liquid-liquid mixture, only sensible heat is there, for phase change from liquid to gas, assuming that liquid is on a cold state, that means it's a sensible heat plus latent heat. That's why the vapor-liquid heat is more greater than the liquid-liquid mixture heat. Thank you.